Good morning, all the participants who join in this meet. Before the start of the first session by Dr. Nagajothi from the ISRO, I just request Basaraju kindly give brief introduction about Nagajothi, sir.
Very good morning to all, and I'm very happy to introduce Dr. K. Nagajothi sir to all of you, who will be the resource person for first session of today. So Dr. Nagajothi is working as scientist, SF, and system manager in Regional Remote Sensing Center, ISRO, Bangalore. Dr. Nagajothi obtained his PhD in computer science in the year 2022 from Bharatiya University, Coimbatore, Tamil Nadu. So Dr. Nagajothi has more than 20 years of work experience in the area of digital image processing, geographical information system, software development, and system administration and system management. And Dr. Nagajothi has expertise in software development and customization for GIS and remote sensing data analysis using open source tools. And Dr. Nagajothi sir is working on geospatial application projects of national mission and large scale user project as a coordinator, team leader that involved design and development of large databases, system integration, customized solution, development using open source and WebGIS, and development of mobile-based application, stereo data processing, and many more. And Dr. Nagajothi sir, current interest involves mathematical morphology, polymetric data analysis and information system, and decision support system. So I welcome Dr. Nagajothi sir again to this event, and I request Dr. Nagajothi sir to take over.
Thank you, Basaraju, and thank you, Syamlal sir. Once again, good morning to all the participants. So in this session, I am trying to cover about the very introductory concepts about the image processing for remote sensing applications. This will be a kind of introduction, basically to bring you all into the onboard to this 5 days workshop. If you see the remote sensing definition, it says we are supposed to study the characteristics about the objects by making observation without coming into physical contact. So that is what the remote sensing definition says. So for this purpose, to make observation about the Earth objects, we employ the electromagnetic energy or the electromagnetic spectrum for detecting and measuring the target characteristics. I think you are all aware about the electromagnetic spectrum. It has got a host of wavelength ranging from gamma rays to radio waves, something like that, and it is split into several regions. What we are seeing with our own eyes is falling within the region of visible region. Okay, so in remote sensing, we mostly employ this visible region of the electromagnetic spectrum. We don't restrict the visible region. We go beyond that also. We take observations on infrared and microwave, and sometimes in radio waves also. So this is the concept behind the remote sensing is totally depending on the electromagnetic spectrum and its the object's behavior in response to the electromagnetic energy which is falling onto the Earth objects. The principle behind this is basically the Earth objects behave differently in different wavelengths. So that is what the characteristic or the character we want to exploit in this remote sensing. For example, if you take the vegetation, which looks green, okay, to our naked eyes, that means the green portion of the wavelength is totally reflected by the vegetation, and the remaining portion of the electromagnetic energy is absorbed by it. So it looks green. But when we employ the remote sensing detectors or sensors, we can realize that the vegetation reflects more in infrared compared to the red region. So this is the typical characteristics of a vegetation in response to the electromagnetic energy falling into its own surface. So we try to devise the sensors which can capture the energy reflected by the vegetation in infrared region also. Similarly, the water reflects only the blue, and the sand reflects almost the white. That means the entire energy is reflected back, something like that. If you see the response of water in infrared region, it totally absorbs. If you can see the right side image, the bottom image, the near infrared region, the water body is totally looking black. That means the entire energy coming in the near infrared region is totally absorbed by the water body. It does not reflect anything in the near infrared. So these kind of characteristics are differing for each one of the objects on their surface, which we want to exploit in our remote sensing observation and analysis. So how do we make measurements using the sensors? Okay, these sensors are nothing but the charge coupled devices. When an electromagnetic energy is falling onto this device converts the electromagnetic energy into the equivalent electrical signal. So we call it as a detector in our remote sensing terminology. So this is the basic device or the sensing mechanism which we employ in making the observations. So this kind of sensors, you can just look into the top. Each sensor is of size in micrometers. Okay, it is a very, very small device. Whatever energy is falling into it, it will convert into electrical signals. So these kind of detectors we arrange in a row. Okay, it's called the line sensors. So number of such detectors we place in a single row and use it in our sensors. For example, our resource set sensor, list 3 of resource set satellite, it is having 6,000 detectors in the band 5. Okay, in its size is 13 micrometer. Similarly, the spot 5 satellite, the panchromatic camera is having 12,000 detectors. 12,000 such detectors, and its size is only 6.5 micrometers. Okay, so this is the size of the detectors which we arrange in a line and use it in a sensor. So now the technology has improved. Nowadays, the present satellites are using two-dimensional array of these sensors. That is called the array sensors. The advantage I will be telling in the next slide. So this kind of array sensors are being used in most of the recent satellites, especially in getting the high resolution satellite images. And another thing is, each of these detector is exposed to the Earth surface for a particular amount of time. That we call it as a integration time. Okay. For example, the Spot 5 sensor, panchromatic sensor is having integration time of 0.752 milliseconds. Okay. So most of the sensors, the integration time is in milliseconds. Means what? So only this much time of time is allowed for the sensors to acquire the energy reflected by the Earth objects. So the array sensors basically what it do is the whatever energy captured by the particular sensor or the particular detector is passed on to the next row in the same line. Similarly, third row, fourth row, fifth row, like that. Depending on the number of rows, each the energy captured by the sensor is passed on, and ultimately it is integrated to a single signal. The advantage is we increase the integration time using this method. For example, if 0.575 millisecond is the integration time of spot. So if we use array sensor, it will be, for example, in this case, 32 rows are there. So we are increasing the integration time by 32 times. That means the overall exposure of the Earth object to the sensor is multiplied by 32 times here. In the sense, we try to get more and more energy reflected by the Earth objects. Ultimately, the signal to noise ratio is better. We'll be getting the better signal for our observation. So that is the idea. So with this technique, our satellites are able to capture very high resolution satellite data. Now the Indian satellites are capable of capturing up to 30 centimeter by 30 centimeter size of objects also into the sensor array. So basically, what once the detector is placed on the platform, and when it captures the energy from the Earth objects, it generates the equivalent electromagnetic signal. So you can see the object here, the black kind of object. If I start scanning from the point A to point B, point A to the left end of the object, the white color is there. That means the entire energy is reflected back by this object. So the electrical signal generated by the detector is high, which is shown on the right side of that object. Okay. So when it touches the left side of the object, it's a black surface. So that means the total energy is absorbed by the object. Nothing is reflected back. So suddenly the signal level drops down to the bare minimum. Okay. And as we go from the left end of the object to the right end of the object, depending on the energy reflected from the Earth object, the signals are varying, and finally it is given back to the readout signal. So once this analog signal is captured by the detector, it is converted into equivalent digital form. That is analog to digital conversion takes place by undergoing two steps. One is the sampling and another one is the quantization. This sampling is the technique which decides the spatial resolution of the satellite. Okay, of course, the digital signal processing principles are used in this. And similarly, the quantization, which is nothing but it will tell about the signal levels when we observe for using the detectors. These signal levels also vary. Sometimes it is 256, sometimes it is 1024, something like that. So depending on the characteristic of the sensor, that means the modulation transfer function and signal to noise ratio, these kind of characteristics are helpful in deciding the number of quantization levels. So ultimately, if you see, when an object is captured by the device or scanned by the device, sensing device, and if you undergo some sampling intervals converted into equivalent quantization levels, the object will look like as shown in the right side image. So in this case, I have some 14 rows and 12 columns. Okay. So if I have the entire range of signal divided into 14 rows and by 12 columns, my object is converted like this. So now you are having kind of a step effect, right? So how do you get the shape of the object similar to the one what we have observed? So for that sake, you have to increase this number of sampling intervals. In turn, the resolution spatial resolution we have to increase, so that the objects represented by the sensor will almost match the shape of the object what we captured the data. So these kind of line sensors, we can have many. Okay, it need not be a one line sensor. We can have a number of such arrays placed in our satellite. So here, what we do is generally we split the electromagnetic spectral region into different wavelengths, right? So, for example, red region alone, green region alone, blue region alone, something like that. So, for each of this region, we design the filters accordingly, so that only that portion of the electromagnetic energy is passed on to the sensor. The remaining portion is knocked off. Okay. So similarly, only the green wavelength is passed on, and blue wavelength is passed on, or infrared region is passed on to the sensors. So like that, you can have different kind of cameras. Each camera will observe the energy reflected by only that portion of the electromagnetic spectrum or wavelength, range of wavelength. So in this picture, you can see the 4 cameras, which is the typical IRS 1C, 1D and resource set cameras, where we have 3 bands: green, blue, red, and infrared. Okay, so 4 camera sensor is put in this place in this picture. So these sensors basically, which can fall into 2 major categories. One is the imaging sensor, wherein the observations are converted into images. Okay, so we get a picture once this sensor is employed for observation. Another one is the non-imaging sensor, which will give you some discrete values only, which you have to analyze in a different form. So these imaging sensors again fall into 2 subtypes. One is the passive sensor and active sensor. The passive sensors depend on the source of energy from other sources. Okay, so it does not have its own source of energy. For example, these sensors what we employ in our remote sensing satellite optical region will depend on the energy supplied by the sun. Okay, so it depends on the solar energy. So these are all called the passive sensors. Some sensors which are operating on the radio wave region or microwave region, they are all called active sensors. These sensors will have its own antenna, which will generate the energy in microwave region or other regions and emanate the energy, receive the energy reflected back by the earth objects. So these are all called the active sensors. Similarly, in non-imaging case also we have these 2 types, passive and active sensors. Generally, the laser sensors what we use, they are all called the active sensor in non-imaging category. So these sensors we can, how do we make the measurements? Okay, so remote sensing, as I told you, you should not come in contact with the earth objects. So we need to place these sensors in some platforms. Okay, these platforms can be on the ground based, for example, ground based spectroradiometer, etc. Or you can put it on the aircraft, which we generally use in aerial remote sensing, or in balloons for some experimental purposes. So nowadays we use these cameras in drones and UAVs also. Okay, and the third one is the space-based platforms, what we are going to talk today's session. So these sensors are placed in the satellites. Okay, these satellites are orbiting in different orbits, and also in space shuttle it is available. So when we talk about the space-based platforms, you know that satellites are revolving around the Earth surface, correct? So most of these remote sensing satellites are placed from low Earth to medium Earth object orbits, which is ranging from 300 to maximum 800 to 1,000 kilometers. So mostly it is operating in the near polar but it is not only polar objects, polar orbits. So remote sensing sensors can also be placed in geostationary orbits. These geostationary orbits are placed, it is around 36,000 kilometers away from the Earth's surface. So the advantage of this geostationary orbit is the orbital velocity or the revolution or orbital period is matching with the Earth's orbital period. That means the satellite also will take 24 hours to make one revolution. So it is in sync with the Earth rotation, so that once the satellite is placed around 36,000 kilometers, it looks stationary for us. So it can continuously beam the signals, receive and beam the signals to the designated area. So now we are planning to employ remote sensing sensors in geostationary satellite also for continuous observations. So one of the example is our GSS satellite, which we are planning to launch shortly, so that we can make observation continuously. Whereas the near polar orbit satellites will take one strip every time it revolves around our Indian region or whichever region is designated, and the area which it is covered or the width it is covered is called the swath. This swath also varies from satellite to satellite. Of course, you will get the details in the website, what kind of sensors, what is its resolution, what is the swath, etc. So ultimately, once we receive the signal using this line array or array sensors and converted analog signals to digital signals, we will get the numbers. Okay, we will get the digital numbers as a part of the digitization. That is arranged in a two-dimensional array. So this is called the digital image. Okay, so this element of this array are called pixel elements, or otherwise in digital image processing terminology, it is pixels. So we have different names for this: gray levels, DN values, pixel, etc. for the same the number. Okay, so each number will represent the quantum of energy reflected by the Earth object on a particular area on the Earth surface. So this is called the digital image. Okay, so pixels, what we call is this is the smallest sample of an image. So more pixel if you have, it translates to the increased details. The digital number, that is the pixel, is stored in a computer in a storage medium and you know that the smallest storage unit is a byte in our computer storage, so which is comprising of 8 bits. Okay, so in 8 bits, if you want to store a number, the number can range from 0 to 255. Otherwise, you can store 256 colors in this 8-bit data. Most of our remote sensings are generating the data in 8 bits, but many of the recent satellites, they are all going beyond the 8 bits. Now they are giving data in 10, 11 bits, etc. And some of our microwave sensors, they give in 32-bit complex data also. So accordingly, the number of colors also will change. For example, if you store in the 16 bits per pixel, you will be able to generate 65,536 colors. Okay. Similarly, 24 bits per pixel will be able to generate 16.7 million colors. Okay. So of course, though the number of colors or the shades can vary, the compromise is the data storage. So you will have to have more and more data storage to store this kind of detailed information. So these sensors, as I told you, can vary from range, wavelength to wavelength. We call some panchromatic sensors, which operates in the entire visible region. That means 0.4 to 0.7 micrometers. So this visible region, the entire energy is captured by the single sensor. Okay. So this is basically generates the black and white image. We call it as a panchromatic. So the chromatic region is pan across. So we call it a panchromatic sensor. And the other sensors which restrict the wavelength to particular wavelength regions like red, blue, green, or infrared, they are all called multispectral bands. Okay, so we can design the sensor either which can operate in panchromatic band or in multispectral band also. These multispectral bands generally have the region around 100 nanometers. It need not be exactly 100 nanometers. The range is within the 100 nanometer region. For example, red is 0.5 to 0.6, and beyond that infrared region, like that. So suppose if we narrow down this wavelength into still finer wavelengths, okay, so instead of 100 nanometer region, if we make it a 5 nanometer region or 10 nanometer region, you'll be able to generate much more bands, okay, much more layers of digital image. This we generally call it as a hyperspectral images. So there are three varieties. One is the panchromatic region, another one is the multispectral, where the number of bands can vary from 4 to 7, 8, 10 like that. So once we generate the digital image in very narrow wavelengths and it is a continuous region, we call it as a hyperspectral. These hyperspectral bands range from 164, 128 to 256 and even 1024 like that. So those many number of images, digital images, you will be able to generate for a particular region of the ground surface. So that is the advantage. This has got some special applications, especially in mineralogy and all those things, and identifying the various crop types and crop condition, etc. Lot of applications using the hyperspectral remote sensing. So this is the typical image which is captured in the panchromatic region by the Cartosat-1 satellite data. And this is of 2.5 meter spatial resolution. What you are seeing is the Bangalore city region where Vidhan Saudha and the race course and other regions are seen here. The same area, when you capture with the resolution of 1 meter, the image looks like this. That means you get more and more detail as you increase the spatial resolution. So now the present satellites of present Indian satellites can capture the data up to 30 centimeter spatial resolution. So the same image, when you look into the color, so that means I have acquired the multispectral remote sensing sensor here. So I acquired the data in green, red, and infrared region here, right? So the red colors, what you see is nothing but the vegetation. As I told you in the beginning, the vegetation reflects more in the infrared region. So most of our sensor design, which is used for agricultural or vegetation related studies, will employ the sensor in the infrared region, okay, which essentially we make use in most of our agricultural applications. So here the infrared spectral band is used. Hello. Yeah. So the vegetation looks green here. Okay. So the multispectral data with 60 centimeter spatial resolution looks like this. Of course, this data is from the QuickBet satellite. Okay, from Digital Globe. So when you talk about the remote sensing data, you come across various terminologies like high resolution, low resolution, multispectral, panchromatic, etc. So basically, the high resolution, what we talk is the images which gives you more and more detail. So the any data which is of resolution 5 meter and above, we generally call it as a high resolution data, and 5 meter and below, we generally call it as a low resolution. So the purpose is you get more and more detail in the high resolution, which essentially you can use for urban planning and some kind of micro level planning. All those things you can use it. Whereas the low resolution data, it is best for the regional phenomena. That means the statistic planning, you can make use of the low resolution data. For example, you can cover the entire nation in 1 or 2 passes of our AWS sensor and use it for the drought kind of studies, etc. So similarly, the multispectral, as I informed you, the objects behave differently in different spectral wavelengths. So based on its characteristics, you can study about different objects using the multispectral data. Whereas the panchromatic data is used as a black and white image, which is also which generally gives in the very high resolution. So most of our satellites, give the panchromatic data in high resolution, whereas the multispectral resolution is slightly lower compared to panchromatic data. So you get all the details about the sensors, what kind of swath, the area it covers, what resolution it gives, what is the periodicity, that means the temporal mode, how frequently it covers the same area. All this information you get from this website called directory.eoportal.org. Not only the Indian satellites, you get the satellites missions across the world. The details you will get in this website. You people can please note down and go through this. The full details you will get in this website. So that is what about the image acquisition part. So we have acquired the digital image using some sensors. So now we bring the data for our computer lab for our analysis. So first thing what we do is we generally try to view the satellite data. So what it has captured, which areas it captured, how the image looks like this, right? So nowadays we are equipped with the color terminals. So we can use the very high resolution color terminals to view the satellite data. The thing is, it can cater only to 3 bands. Okay, so the color monitors have red, green, and blue guns, right? So that means at a time you will be able to display only 3 bands of the multispectral data what you have captured. So your multispectral data can vary from 3 bands, 4 bands, 7 bands, 10 bands, etc. But out of the 10 bands, you should be able to choose only 3 bands for the color combination used by the terminal, right? So this is the kind of data. If you change the band combination, the image also it looks different. This is basically exploited by the different subject people. For example, the geology people will try to introduce the thermal portion of the electromagnetic energy or thermal data, and the agricultural person will employ the infrared region, etc. So like that, each discipline people will use the different spectral band image data. So based on their requirement, they can use this color combination to view the satellite data. So now, finally, we'll move into how do we process these digital images once is given to us. Okay. So what is this goal of this image processing? So the digital image processing is basically to mimic or replace the human visual system. That means by looking at the digital image, what are the information we infer, we should be able to get it from the computer algorithms, okay, automatically or repeatedly. So that is what we are planning. We are supposed to exploit from the image processing techniques. And also it helps in humans in interpreting the visual data. As I told you, you can have different band combinations, different spectral band data can use, interpret it for deriving the information related to various domains. Okay. So the major functionality, if you see in this image processing, we try to restore or pre-process the image as soon as the data is given to you. And then we go for the image enhancements, where we try to improve the image quality. And finally, we interpret the image and analyze it for inferring some information from the digital image for our study area. So the sequence of steps will be like this. We get the input data, we pre-process the data to make it amenable for our interpretation and analysis. Then we go for the image processing techniques. It could be rectification, registration, or enhancement, or classification, or whatever it is. Finally, once the image is interpreted or analyzed, it will undergo some post-processing techniques to give the information in the usable form. That means the whatever information we generate out of this image processing technique can be presented in the form of maps or something, or the digital images to other users for implementation or executing some projects. So that is what the basic, the major 3 steps in this digital image processing. We'll just go through one by one a little bit detail. So the pre-processing, why it is required? Okay. So we talked about the satellite platforms, which is around 300 to 800 kilometers away from the Earth surface, and these platforms are revolving around the Earth surface. It is monitored continually to keep the satellite in that particular orbit, so that we get the image captured for the intended area, study area, right? So these orbits can undergo some disturbances due to atmospheric drag. Okay, so in that height, though the atmosphere role is very less, but still we have some micro effects of the atmosphere, Earth's atmosphere. So it drags the satellite orbit little bit. In the sense, the orbits can come down by its altitude by a few centimeters or millimeters or so. Okay, so once the orbit comes down, the area what it covers will reduce accordingly. Your intended area will not be able to capture. And similarly, the Earth surface, it is not the perfect globe, as you are aware. It is flattened in the pole regions. That also creates some problem in maintaining this orbit accurately. Then apart from that, you have the effect on gravitational pull of the sun and moon also. Okay, you must be surprising whether it has any effect. Yes, the sun and moon's gravitational pull also has some effect on maintaining this orbit. And the fourth one is the solar radiation pressure. And you all must be aware, all our satellites generates its own power using the solar panels. Okay, as soon as the satellite is placed in the orbit, the solar panels are deployed. It generates the power using the solar energy, right? So the photons. So when we consider the electromagnetic energy as a particle, so we talk about the photons. So each photon is having its own mass and the velocity. When it falls on the solar panel, it generates a momentum of 2 MV, right? So this is sufficient to disturbance the position of the satellite by a bit. Okay, so these are certain things which disturb the orbits and its position. Which will introduce some errors in our digital image. So these are the things which can be corrected by knowing the satellite's position and whatever it is. We call it as health data. We correct the images using these pre-processing techniques. So we correct for its geometry of the image. We also correct the radiometry. That is nothing but the measured pixel values. And in case if any noise is introduced because of the malfunctioning of the sensing devices, we also correct it during these pre-processing stages. So this required some amount of information from the satellite itself and also the sensor characteristics. So that is the reason most of the pre-processing steps are carried out by the data providing agency itself. For example, in our Indian satellite scenario, all this pre-processing is done at the National Remote Sensing Center, where they capture the data, where they archive the data, they correct for all these errors and give ultimately the data usable form to you, okay, to any user rather. So in the apart from geometry, we also correct for the radiometry. So radiometry correction is important because the solar energy is passing through the atmosphere and it falls on the Earth object. Again, it is reflected back. The portion of the energy rather is reflected back to the sensing device, okay, or the sensor mounted on the aircraft or satellite, right? So when it passes through the atmosphere, it undergoes some disturbance, right? So these atmospheric parameters are required to correct the radiometry or to correct the measured pixel values, so that we exactly get what exactly the energy reflected by a particular Earth object. So this is called the atmospheric correction. Of course, when you go through the digital image processing techniques, you will come across the various algorithms available for this atmospheric correction. So what we are trying to do is we try to nullify the effects induced by the atmosphere and to get the actual energy fall on the Earth surface and the actual energy reflected by the Earth surface. These things we achieve by correcting the radiometry. And the second step is the enhancing image. So why this enhancement is required? So it is basically to improve the appearance of the image so that it is amenable for human visual analysis, right? So when you display the image, obviously you will know what area has been covered, what are the features, how it is represented on this digital image, right? So when you want to do some kind of visual interpretation, the image should be pleasing, right? So these enhancement techniques are helpful in making the image in its appearance better. Okay. So in these things, you are doing three things. You are highlighting the interesting details in the images. For example, if you are interested in only the building area, of the urban area, you can just enhance only the buildings and you can just make it dull the other regions also. Similarly, if you want to study about the linear networks like roads or rails or the drainage networks, you can enhance only that kind of features, linear features, and suppress the other features. So some features can be highlighted, some features can be suppressed also. And also you can remove some kind of noise, if at all, if it is part of your digital image, what you have got it. And also you can make the images more visually appealing. So here we employ two categories of algorithms based on the spatial domain techniques. So you can directly manipulate the digital numbers, what you got in the digital image. Another one is the frequency domain techniques, where we employed Fourier transformation or wavelet transformation for making some kind of enhancement in this image. So what are the different enhancement techniques? I'll just touch upon only one example, which is called the contrast enhancement, right? So remaining things you can just go through because it is this lecture is only the introduction part. So if you just look at the pixel values, what you got from your digital image by plotting the histogram. This histogram is nothing but the graph which represents the number of gray levels and the frequency of its occurrence in a graphical form. So if you see in this slide, the red color is the histogram. What I got from a typical image, right? And the left side of the graph is the value 0, and the right end of the graph is the value 255. For example, I'm telling here. So this is the 8-bit data. So in this 8-bit data, I don't have the values ranging from 0 to 255. My pixel levels are narrowed down to some region. For example, here, let us say it is 50 from 150 only. So remaining portions are empty, right? So when we display this image in the computer monitor, all these pixel values are cluttered. We will not be in a position to differentiate the different shades represented by these gray levels. Okay, our human eye can differentiate only 12 to 14 shades, not beyond that. the pixel values can range from 0 to 255. But when it is represented in the monitor as a black and white image with the shades of gray, our eye cannot differentiate more than 12 to 14 shades, right? So to make the shades more differentiable, we try to increase the contrast. So the contrast is nothing but the differentiable shades, right? So some of the techniques are available, many algorithms are available to enhance the image using this contrast enhancement technique. So you can see this image in the left top corner is the raw data or the data what I got from the data providing agency. My image looks like this, and when I generate the histogram, you can see on the right side the histogram is cluttered into a narrow region, right? So I can use the contrast enhancement techniques to improve its visible appearance. I have used one of the technique called linear stretch. The formula is given here in the bottom of the screen. So using this formula, I can enhance the histogram so that it occupies the full range of the display region. So now from 50 to 150, I have expanded this histogram, or I have modified this gray level to fill the display region, full display region, that is ranging from 0 to 255. So in this case, what happened? The distance between the gray levels have increased a little bit, so that the contrast is increased. So the shades are distinguishable now, the contrast is increased. So this is what the technique we apply in contrast enhancement. So there are several algorithms available under contrast enhancements. This is only one example, the very preliminary example what I have shown you. So when you use any of these image processing packages, you will have a host of algorithms already implemented on this. The second technique what we use is the frequency based, right? So in this case, we will be employing the technique called spatial frequency. Okay, the spatial frequency is nothing but the number of changes in gray level. For example, in this case, you take a urban area, so where you have road, then adjacent to that some buildings are there. Again, road will come, again buildings, like that. So that means when I capture the data, so frequently I'll be observing building, road, building, road, building, road, etc. So number of changes in gray level will vary because roads reflects a different energy level, building reflects a different energy level. So this kind of changes in gray levels are called edges in our digital image, right? So if you have more edges, that is called the high frequency data. If you have less edges, like shown in the left side of this picture, it is called the low frequency data. So this spatial frequency is exploited in our employing our Fourier and wavelet transformation techniques to improve or enhance the images. So you can once you have the frequency, you can design the filters which can work in some way. In the sense, it can pass only the low frequency images or low frequency pixels or low frequency area in the output, or it can pass only the high frequency pixels in your output area. So these are all called low pass and high pass filters. So in this way, you will be able to enhance only some portion of the image or some features of the image by spatial techniques. So another thing is when I talked about you can highlight only some features of the image. So for this we employ the technique called spatial filtering, right? So it is nothing but it works on the convolution technique, which is the key principle in our artificial intelligence or neural network based algorithms like CNN, etc. Where you are having the small matrix, let us say 3 by 3 or 5 by 5. This matrix will contain the weightages. Okay, this matrix will contain the weightages. This smaller matrix will be moved around or convolved around the bigger matrix. Our bigger matrix is the digital image. So this smaller matrix will be convolved over the bigger image. The output values will be calculated as per the weightages, and the output is given. So using these techniques, you can highlight certain features. You can highlight the edges or the features like what is shown in this picture. Some building area is highlighted. Similarly, you can highlight the features which is falling in certain direction also. For example, northwest or northeast, southeast, southwest, like that. So you can design the filters suitably to enhance the features falling in certain directions, or only the features which are linear in nature. So all these techniques are possible using this spatial filtering technique. The third way of increasing the contrast or enhancing the image is using the image fusion. As I told you, as I mentioned earlier, the panoramic images generally it is of high resolution, And the multispectral data, it is generally of low resolution compared to panchromatic data. So the panchromatic data obviously will have the more detail or in a finer details, and the multispectral data will have lesser information but in color, right? So if you want to see the images in color and also in a very detailed manner, you can merge the panchromatic data with this multispectral data. This technique is called the image fusion. Okay, so in this technique, the spatial information or the brightness values from panchromatic data is picked up using the several algorithms available. Here also we use the wavelet transformation, etc., to fuse the image, the panchromatic black and white image with the multispectral image. Ultimately, you will get the color image with high resolution. Okay, so that is what the idea using this image fusion. So whatever is happening so far, these are all the systematic errors, the errors which we know based on the satellites orbit, attitude and altitude, etc., which is either corrected by the image data processing image generating agency or by our own algorithms in the lab. And some errors are non-systematic. Okay, so sudden changes in altitude and attitude in the sense the roll pitch of the platform. So this will introduce some kind of errors. It shall happen at that moment, okay, which cannot be predicted in advance. So these are all called non-systematic errors. These errors we correct in our lab using the technique called image rectification or registration. So what we generally do here is we try to reference our image with a known map coordinate systems. That means we try to register the image what we get from the survey of India topo sheets or the latitude longitude coordinate system, etc., so that the image is brought in line or it is registered with the earth surface features. So generally the digital image when we get is nothing but two-dimensional array of pixels which will have only the image coordinates. Each pixel you will get only the digital number, nothing else. So when we reference this with a map coordinate system, each pixel will get associated with its own latitude and longitude values. Okay, so that the image itself can be used as a map once this process is undergone, right? So you can see the rectangular image, which is slightly turned into, which is skewed. Once I do this reference into the map coordinate system, this is happened because of the Earth rotation, right? As the satellite scans from top to bottom or north to south, by the time it scans from the top north portion to south portion, Earth would have already rotated to some extent. So once we register this with the map coordinate system, this Earth rotation correction is compensated, and that's why you get the image skewed like this. So why it is required, the registering into the common map coordinate system? When you want to study the changes, what has happened in a particular area over a period of time. Of course, using the satellite platforms or air platforms, you can capture the data of same area in multiple periods. Okay, that is called the temporal data. So if we want to identify what has happened, what the changes happened in a particular area, I can capture the same area in a different time period and register this image one-to-one and find out what exactly happened in pixel to pixel basis. You can find out the changes. So this change monitoring is the upcoming or the hot topic nowadays. Most of the projects would like to monitor the changes, what has happened. Okay, not only in the urban areas, even in other water set level planning and execution, they want to monitor the project progress by using this change monitoring technique. So including the highway projects, all those things. So this is one of the hot topics where the change monitoring is one of the very, very essential or useful component in digital image processing. And finally, we want to infer some information from the digital images. So for this, we use the technique called digital image classification. So wherein each pixel is assigned to some of the or each pixel is labeled to some categories. Okay, it could be the land use, land cover. For example, each pixel is associated to vegetation or building or water body or open area, something like that. Okay, or forest, etc. So, right. So using this process, we try to label the pixels into the particular land use category or any of the domain classes, right? So this is the process of assigning individual pixel of a multispectral image in discrete categories. So for this purpose, we clutter the pixels into particular categories. Right? These clusters are then assigned to a thematic class or any labels. So what we generally do is, you know, the vegetation, it reflects, for example, forest, if you take, it will look a different color. The crop area, paddy or wheat will look in different color. The plantations, let us say cashew nut or mango or coconut or coconut will look different color. So if your satellite is capable of, or if your sensor is capable of capturing this kind of different objects in your multispectral data, you can always go for identifying the different crop types also. Otherwise, you can always group all this vegetation into a single class called a vegetation, right? So anything which is looking red in my digital image, I will put it into the class called vegetation. And similarly, the urban areas, whatever may be the kind of reflection from the buildings, high rise or slum area buildings, you can group into the urban category. Similarly, the water, whether it is shallow or deep water, you can put it into the single class called the water, right? So depending on your interpretation skills, depending on the sensor characteristics, you can go into the subtypes into each one of these categories and get into the finer and finer details in your classified map. So here in this example, I have only 3 classes: vegetation, urban, and water. So ultimately, the image, what you captured in the multispectral, will result into a classified map, wherein I will have the single image or single band data with only 3 numbers, one number representing urban, another number representing water, another number representing vegetation. So this is what the classification process is doing in this digital image processing technique. So if you look into the algorithms, of course, this is one of the very important category which leads into your AI-based techniques like machine learning and deep learning. I think you will be exposed to all these algorithms in the future lectures. Basically, this classification algorithm falls into 2 categories. First one is unsupervised, wherein we don't have any knowledge about the surface or that surface or the study area of our digital image. So in this case, we totally rely upon the computer algorithms to make the groups or clusters and ultimately result into the particular categories. So what we can achieve here is, you just subject on digital image into unsupervised classification algorithm, and you can tell the computer, I wanted 10 classes out of this image. So it will generate based on the spectral response or spectral information available in the digital image. It will give you the 10 spectral classes. So that's what it will do. So afterwards, it is your problem to interpret what are the classes. Each class falls into which of the land use or land cover category. So that is left to interpreter. Okay. So that is what the unsupervised classification algorithm does. The second and major category is the supervised classification. So here you require some ground knowledge. So as I told you in the previous slide, suppose you know the response given by the coconut plantation, you know the response given by the paddy field, you know the response given by the mango field. So you can always tell or train the computer by marking those areas and tell that this area belongs to coconut, this area belongs to mango, this area belongs to paddy, or this area belongs to shallow water or deep water or salty area, something like that. So this kind of training you give to the computer algorithm. So based on the training samples, what is given by the interpreter or the analyst, the algorithm will consider those training pixels into consideration and try to classify the unknown pixels into that particular category. Okay, so this is very, very important. And host of algorithms are available into supervised category. Many of the operational projects will use this kind of supervised classification only. If you see the process, you get the raw data. Of course, this is animation, which I am not able to show you because of the PDF file. So you get the raw data, you go for collecting the signature or the training samples, right? And you have some algorithms to evaluate these training signatures. Okay, so whether whatever training samples you are given is correct or not, you can evaluate it, and ultimately you can subject these training samples into classification algorithm, and finally you get the classified map. You can always measure the accuracy of your classified maps and refine it. So this is what the process of classification. So that's all about the basic digital image processing techniques as far as optical data is concerned. And now much more things are happening. So I want to just touch upon one or two slides about the other digital image processing techniques also. Another important thing is the satellite photogrammetry, right? So you all know about the Earth is a 3-dimensional globe. okay, where height is also one of the important component. It is not that when you capture the Earth surface, only the surface features and its elevation or the terrain information also very important. So how do we get the height information? Okay, so that technique is called the photogrammetry. Of course, earlier people are using the aircrafts. They capture the digital images, use it in the lab using the technique called photogrammetry. Those were analog photogrammetries. Afterwards, it is emerged into digital photogrammetry, and finally, we are talking about the satellite photogrammetry. So here, what we are trying to exploit is using this relief displacement. Okay, so this displacement is nothing but the position of the image pixel of an object in the image is displaced because of the height of an object. You can see in this picture, I have a Eiffel Tower, right? Eiffel Tower has got its base, rectangular base, and its tip on the top portion is shown here, right? So if I capture the digital image, it is the representation of the digital Eiffel Tower and its surroundings. This is a two-dimensional matrix, correct? So if I just look at the position of this tip of this Eiffel Tower, it is somewhere on the top. Okay, if I see the image coordinates, it is somewhere falling into, let us say, 50th row by 75 pixels, something like that. But its actual position is supposed to be on the middle of this base, correct? As far if I look at the Eiffel Tower from the orthographic projection or in the Nadir view, I will have the image position of the tip of the tower exactly on the middle of its base, right? But when I capture like this, the tip of the Eiffel Tower is not placed on the middle of the base, it is somewhere placed. This is called the relief displacement. So this displacement of representation of this image object in a digital image will vary depending on the height. So this displacement we want to exploit and find out the height of the objects, right? So for this, what we do is we capture the same image or the same area from two different angles. Okay, so let us say one from the left side, another from the right side. Of course, you have some criteria for this. What should be the baseline difference? What should be the height to height ratio and all those things, base to height ratio, etc. So based on that, we try to capture the digital image from two different angles, and the objects represented on this digital image, the position will vary in the digital image. So this change in position is called the parallax. By estimating the parallax, we will be in a position to identify the height of the object. So this is the basic photogrammetry principle. So we call it as a stereo pair. The same area captured in two different angles. By identifying, by estimating the parallax or the change in image positions, we try to associate the change in image position or the parallax value to the height, and ultimately we get the three-dimensional data. So this kind of data is already generated for the entire globe, and especially using our Indian satellite, we have generated the digital elevation model or the terrain elevation information. We have already populated this data in our portal called Bhuvan. So you'll be able to see the three-dimensional perspective view once you go to Bhuvan site. So this is the typical example of Himalayan region where you can see the peaks and pits of the hilly region using this digital elevation model. Of course, this digital elevation model or the height information, the number of applications are plenty in in civil engineering and in in the disaster management, like flood management, flood monitoring, etc., or especially by the military people for visibility analysis and identifying their strategic position, etc. A lot of applications are possible with the digital elevation model data. And the third one is the microwave remote sensing. So in the optical remote sensing, we capture the data. We will be able to see the Earth objects represented on the digital image by our own eyes, no problem, right? So whenever there is rain or the monsoon season, the cloud is there, the optical sensors are not capable of passing through the clouds and see the Earth surface features. Okay, so in that case, we will not be in a position to capture the data during the monsoon or the cloud cover is there. So in that case, we move our sensors, to operate on a microwave region of the electromagnetic spectrum. Right. So in this, the advantage is these wavelengths can penetrate the cloud. Okay, it can penetrate the cloud. It can penetrate even the tiny droplets of the rain, etc. And it can even penetrate the ground surface to some extent. Depending on the wavelength, it can penetrate up to 15 to 30 centimeters, etc. Depending on the wavelength what we use in our microwave remote sensing sensors. So the advantage is you can capture the data even during the cloud cover, even during the rain, even during the night time. So because it is generating its own energy, it doesn't depend on the solar energy or any other source, right? It generates its own energy in the micro region, emanate that energy to the Earth surface, get the, record the energy reflected by the Earth objects. So this can operate in any time, day and night operation is possible. It can pass through cloud also. So that's why most of our defense applications, they use the sensors operating in the micro region. Only thing is the data will not look like our optical data. So interpreting this data will be very, very difficult. Of course, the commercial packages support you with the host of algorithms to process or analyze this micro data also. The fourth one is the laser based, right? So it is a LIDAR, which operates in any of these optical wavelengths only, but it uses the laser beam. So generally, these sensors are mounted either on the UAV or drone or aircrafts only, so far not on the satellites. Okay, so what it does is it emanates the laser beams towards Earth surface and the records the reflected signals, laser signals by the aircraft. The advantage is you'll be able to generate very high resolution data using this, and mainly it is used to estimate the height of the Earth objects, especially the buildings or canopy heights or forest vegetation, etc. The accuracy using this method will be very, very high, of the order of centimeters. Okay, so whereas the digital elevation model, what we generate using the photogrammetry principle, will be of the order of few meters, let us say 8 meters or 15 meters, etc. Whereas in this case, you will be able to generate a very accurate elevation information or height information of the order of accuracy to the level of centimeters. So that is the advantages, but it is a costly affair. It is done only for the smaller areas with the due permissions acquired from the defense agency, etc. So next we move into what kind of processing needs are required when we for processing the digital images. I just quoted a small example of Karnataka state. So the Karnataka state total geographical area is close to 2 lakh square kilometers, and the number of districts, of course, it is changed now. It is older information. It is 33 or so. So when we acquire the digital image using the Kato-1 satellite data, I have to acquire 460 scenes to cover the entire Karnataka state. Okay, this will occupy around 165 GB on a disk space. And if I take the panchromatic data of list sensor, panchromatic sensor, I will have to acquire 80 scenes, which will occupy 20 GB. Similarly, the multispectral data of list 3 sensor around 23 meters spatial resolution, I need 30 scenes. And list 4 with 5.8 meter spatial resolution multispectral data, only for 3 bands, I require 800 scenes. Okay, so ultimately, if you see, the raw data alone will occupy around 1.3 TB, right? So once you get these kind of pieces, you have to register into the map coordinate system and then mosaic into cover the entire study area. Afterwards, you will go for some enhancements. You will try to do some analysis, all those things. So which will require multiple times of this raw data in your storage requirement. So this I am telling specifically as and when you go for higher and higher resolution data, your storage requirements also will be more. And once you start processing the data using your network or internet, your bandwidth also will increase. So suitably, you have to design your hardware to cater to your processing needs. So what are the different challenges? So interpreting images require the prior knowledge, which is not present in the image. That means the interpreters should also expected to have some knowledge about what are the spectral bands used, how the objects will behave in each of the spectral bands, which area is covered, what kind of objects are available. This kind of prior knowledge is a little bit essential to interpret the image. And another thing is the patterns describing objects are not fixed and depend on the environmental effects. That means once you see the vegetation one time, it is represented as some kind of red patch. It is not always the same patch when we capture the same area in different environmental conditions. So depending on the solar radiation or solar illumination conditions, the angle which you view, the characteristic of the sensor, the things, the pixel values will change, okay, or the characteristic of the digital image will change. So this is one of the problems. So you have to compensate. Basically, you have to normalize the image for different seasons, capture in different season, okay. And also the complications arising from the need for geometric model and the cognitive processing of visual information to achieve the capability to mimic the biological visual systems. So basically, no, you need to do some geometric modeling and the cognitive processing so that it can mimic the biological visual systems. And impairments of data acquisition systems that results in noise and incomplete data. This happens mainly because of the malfunctioning of the detectors, right? So the detectors also will wear and tear over the time, right? The same sensing device after 5 or 6 years, its performance will decrease or degrade. So of course, this is always compensated by the data processing agency by changing the bias and gain values. But still, some errors can be introduced, some noise can be introduced by the digital image by this sensing device malfunctioning, which is to be compensated. And the next is the complexities due to integrating visual information from data from other external sources. So when I talked about registering into common map coordinate system, with this technique, you can always register that data acquired from other sources also, right? For example, the field collected data or the information acquired by other satellites or other platforms like UAV or drone, etc. So when we try to integrate, some complexities that will arise. Okay, so this has to be taken into consideration, and the processing time necessary for dealing with the enormous bulk or visual data. As I mentioned in the previous slide, the volume increases accordingly. Your processing time or the processing speed of the processor what we use in your computer also has to be suitably designed to analyze images to get us some results. And the recent trends in this digital image processing is the natural man-made interfaces, and we also know about the augmented and mixed reality. You have robotics, which uses the computer vision for this kind of applications. You have intelligent transportation system, which is used in managing the traffic and all those things. And surveillance for security, we know from CCTV cameras onwards, everywhere the image processing is used, not only during daytime, even the night image is also used for this purpose. And non-invasive medical systems. Okay, so this digital image processing is not restricted only to the remote sensing data. We know very well the medical field is also one of the very major user of this digital image processing. Whereas CT scan, MRI, etc., are all using this image processing techniques. And nowadays you have got the plug and play vision systems also for gaming and other devices. So apart from that, of course, now we are also moving towards AI techniques using machine learning and deep learning. We are trying to infer and get more and more information from this remote sensing data. Yeah, I think that's all about the basics of digital image processing. I hope I have made the things a little bit clear to you.